Yeah, no, 1 second. 1 second.
Got it.
Yeah. Hi, everyone.
Hi, everyone.
This is Andrei, Kirk, and Nikolai once again with Postgres Hacking session. I need to mute myself here. Okay. So we start many things. Of course, not all of them make it to like main branch, I would say, right? But it's okay, right? Some kind of experiments. And last time we had experiments with pg.kcache. We created pull request, and the pg.kcache maintainer commented. So let's start from there, right? You, like, Andrei, what do you think? Do we have some chances to be contribution accepted?
Julian proposes better refactoring towards like less locks in hash table. Like let
me remind quickly. We saw contention which was caused by the attempt when new entry should be created in pg.kcache, and our optimization was very trivial. Let's try our best during some microseconds, and it doesn't work. We just skip inserting. We'll try next time, right? So Julian says it's a kind of not a good idea, maybe, right? And I remember one of the points also is that pg.statements code is kind of the same, so it should be done there as well.
Exactly. It's exactly the same structure of locks and storages, and like it's different resource measuring, but the same framework to store results.
So and again, just to recap a little bit for the slower people like me, the cause of this is in order to make pg.stat statements fast, it doesn't use a table. It uses an in-memory hash kind of structure. And it has to, when someone's requesting data from it, it has to kind of lock that because it can't be walking through this structure while someone's modifying it. The flip side is that whenever a new SQL statement is being created, you have to lock it so that you can add to it. And this is where the contention comes from. In a busy system, you have this thing being updated a lot. In a busy system where you're actually requesting data from it, and the time it takes that data to come back is long, then you place a lock on it longer. And this actually did, now just mention this, I thought of a second thing where what if we had an overflow structure? So instead of throwing away the SQL, we added it to another hash table that would have far less contention. And then the first time we were able to acquire the lock and add a new SQL statement or whatever, then we could actually check to see if this other hash table was not empty. And if it wasn't, we could quickly add those items and clear out that.
To build a queue, right?
Right. Effectively build a queue of the things waiting to get into the hash table. It was just a random idea, but it's like, it defeats the issue that was raised that it's kind of wrong to not log the SQL and to just lose it. But the flip side is what it gets away with is if we just store it somewhere else, and because that cache will be less likely to be held onto for a long time. Nobody is doing queries against it. And you wouldn't access it when you're doing a long query. So when you do get final access to it, you could actually just take that, drop it in, and zap it back out. So anyways, Andrei, I see you smiling. It makes me feel like I'm a good student.
Yeah, this like you're a good inventor. this is like I understand that's like it's not a real invention, right? Right from the mind. You saw it somewhere and applied it here, and the design overall looks like something that we can implement maybe.
And then background worker with consumer of this queue fully asynchronous work.
Just opportunistically, whenever we have this exclusive lock, so we have a backend local cache, and we dump this cache when
we acquire the lock for good. When we get the lock to add anybody new, we also go, oh, and was anybody else delayed? Was there anyone queued before us? And then that's when we add it.
Any limits to this queue? Like how many items can be there.
I'll be honest. My first hacker thought was to make this queue an exact replica of the existing one, so that inserting into it would be trivial. So we basically do the same work, but we just point to a different queue. And then later on, we just move those elements from one to the other and clear it out. That was my first thought, not knowing the structure.
Sense. But in this case, like imagine that we cannot enter this hash table, and every single backend now have a local copy of this entry.
Oh no, I was thinking about storing it in the same, like storing it just like the existing PG stat statement hash table. That's stored in shared memory. This one would be
one more global.
Yeah, another global. Yeah, it would be a global. Boom.
But without not supporting updates, only inserts, like append only some.
Right. Just inserts, just appending to it until we compress it and move it into the other global.
So imagine we have two hash tables.
Mm-hmm.
If one is busy, we are inserting to another.
Yes.
That's exactly what Julian is proposing, actually.
Really?
Ah!
Nice.
Okay. Not like
dumb luck on my part then.
It's not copy paste what he's proposing. He's proposing to use dynamically sharded DS hash, which is splitting a hash table into partitions, and each partition has its own lock. And effectively, it means that we have 16 different hash tables, and we are entering one if it's not locked. No, it's not exactly the same idea. It's a similar idea, like having more fine-grained exclusive lock on part of a hash table. And initially, I understood you like if you are proposing to having a local cache, like for example, how to
an overflow, and just an overflow table until you're ready, like a queue, like Nikolai said.
Imagine if you are doing incrementation, how to increment like counter fast. You can lock it and increment from you are doing it from different processes, different threads.
Right.
You can lock it, or you can have a local counter, which is doing local increments and so on. And when it has locks, it is adding its own local count to global count. And this scales slightly better, but it's more memory. Like we now have this counter for every thread, every process, and the same goes with having a local hash table for every backend.
Yeah, that's how come I was actually thinking two globals. I was thinking the global always create two, one which contains everybody, and one which is overflow and always empty, basically. Mm-hmm. And then basically, if we can acquire the lock to the main one, we should be able to acquire the lock to the second one, because that is never held for any significant length of time. And then we just insert into that and wait to catch up later. And then merge them. So don't collect stats into it. Don't do anything else. Let it sit there, then merge them at the next line.
The problem I see here, it might have duplicates with additional global structure. It might have like multiple queries were like normalized queries the same. So we inserted multiple times. So we need to aggregate them and have not one call, but multiple calls, like n calls already. But like if original structure is not available for a lock for a very long time, this second one can grow significantly, right? It can have
not a big deal. We had to grow original anyway, so second will never be bigger than first might be.
Why not? If it's very long, if we agree not to update but only insert, again, we can have duplicated normalized queries.
If we have an entry somewhere, we just adding stats for this entry. We are not like we enter this query ID, and then we add the call statistics.
Okay.
If the query ID is already in the table, we don't add it. So we avoid the duplicate on that first pass. This is only in the case that we check.
Right.
It's not already in the table. Now we're just going to store it to the side. And the only time the slowdown happens that would trip this code is when the existing list is long enough that getting the stats out of it is slow enough that the lock persists long enough. Right. And then go ahead.
If it happens for a long time and we have two sessions running the same query, which is not present in the main structure yet, we need to insert twice, right?
Well, hold on.
Secondary structure.
Yeah, the twist was if we use a clone of the original structure, we can use a pointer to the structure on the insert, and we can actually do the same logic where we check to see if this SQL ID is already in the structure before we add it again, because it's the same structure.
Okay. So
and then so then this way we could actually have it so that boom. Oh, this is crazy. In a weird way, we could write this similar to what the hacker said in a recursive format where it actually constructs the next one if this one's locked. And it just, right, but that gets a little crazy. But that would give you dynamic partitioning in a way that would be collapsing as the lock's freed up. That would be interesting. Wow. But yeah, it's a little mind-blowing. This is where you start drawing on a board.
yeah, I'm doing it all the day and night. But then when the user is asking for statistics, we have to merge them all anyway.
Well, no, actually, I was just thinking of not losing the statistics and not tracking any in the second global. The point being is that we have to wait for the system to free up with some time before we can, actually merge those in. I wasn't looking at collecting stats in each of these global structures and then merging, but that's an interesting idea. It does complicate things, right? Because now every place where you access the main structure, and then I don't like that either, because technically if you select from stat statements, if you say you're going to be collecting here, if you're busy selecting from it and you start having to lock this second one in order to display data from it, then you're just pushing the problem in the horizon problem. So my thing was, it's just a queue to wait to collect so that the SQL IDs make it in without crashing. Go ahead.
Boil this idea somehow to something we can implement in our when we are hacking on this Thursday hacking session. Like make it still the same, but simple enough to be able to implement it. Because now it sounds like it's doable, certainly doable, but not in.
I think it's worth thinking about it additionally in background, like mind homework, homework from mind.
Yeah, and exactly. I think that's the right approach to kind of hone it down and argue it out a little bit, right? Mm-hmm. And then see if I think once we get there, we might be able to find the real question is it okay to log the SQL IDs without tracking anything else in them in this side buffer until we get that chance to update and then put it in, and then PG stat statements can work its magic on it once it makes it into the main queue. That's the real question for me. If that's not acceptable, then it's probably not worth, traveling down this path.
Like there might be all kinds of races, like one process is able to enter, another is not seen, is that it's entered, and we definitely can have the same query in both hash tables.
How could
races?
Hold on. How does the same query get in both hash tables? Because we would never try to send it into the second hash table if it wasn't already in the first one.
Like It's time to check to time of use. We try to find it in first hash table.
Right.
It's not there. We try to look first hash table. We can't. It's busy. Someone is holding shared lock.
Right.
We try to lock it in second. And at this point, we might be racing with other thread that got a lock on first hash table and successfully entering information into first hash table. So I'm certain that here is a race when the query will end up in both hash tables, and it's unavoidable.
Okay, so then here's the only other piece. Then when we collapse the two tables together, we just double check that we're not inserting the duplicate.
It's totally fine to have a duplicate. Yep. We just add the numbers. They are additive. We can like merge the number of calls, number of pages written, and all the hit misses and whatever key cache is calculating. It's all the numbers that can be added. I think so.
Well, I wasn't talking about ever updating the other one, the queue. Right? The one that's the queue, the secondary one, I wasn't talking about having pgstat statements updated. I was only talking about modifying that one block of code that we were working on in the past, right? That actually checked for the lock. If it got the lock, if it can't get the lock, it logs it here. Can't get the lock, it logs it here to be added later. When it does get the lock, the first thing it does is it says, oh, is this empty? If this is not empty, let me add these in before myself. And while I'm doing that, if I see myself in that list already, then I know not to bother adding myself. Okay. And then we zero that overflow out and we stop there. And now it's updated. So I was literally, so for me, I was thinking it was kind of doable in an hour because we'd focus on that code only. We would never update the statistics in this other structure. There'd be nothing to add. Okay. What we're talking about doing is not losing the SQL ID and when it was initially put in, but we're not talking about being able to track it. And this is probably where it differs from what the other hacker was talking about by setting up some kind of partitioning.
Yeah, we have also comments in chat. Thank you guys for participating. And the question is like, not comment. How about writing an TLA plus model to check for races that Andrei is talking about? I mean, he's now trying to predict races, but model checker could find them.
Like TLA plus is good to prove that there are no races, but we would like to embrace races. Let the concurrency thrive through our database. Let the CPUs run, and something will win in this race.
Well, anyway, are we going to switch to different topic, or we are going to like because this is super interesting, but we wanted to do something else today additionally, right?
Yeah. I think talking about compression is right. Is that where we're going next? So I'll leave this out because I kind of threw it out there. The thought is LZ, Limpelzev, did their first compression, and as they went along, they created a dictionary. So you needed the compressed file and a dictionary. When LZW, Welch, came along and added to it, what he realized is if you don't substitute the first instance of each dictionary item, if you don't do that first substitution, but you just record it as you're going through the string, then what happens is you don't actually have to create a dictionary. And that simplified and reduces potentially the size here. So in my book, the first thought was columns of data tend to have repetitive data in it, which is great. And you wouldn't want to use Limpelzev Welch version because the replicated data doesn't get much smaller, especially on smaller columns. But if you had a dictionary that, for example, had the 20 top values in that column, then if you had that dictionary, then all of a sudden those column values compress very well because they're typically just keys that were looked up. And for example, if it was titles, Mr., Mrs., whatever, and you had a billion rows of these, now instead of storing, 4 bytes, you're storing 1. whatever. So that was where my head started. And then Andre kicked in as well and said, well, we could do this for the entire table across multiple columns. And then we had some discussion. So Andre, I'll let you pick up from there. So that was a rough introduction into compression. And then you know more about compression in other places, everything else.
For naive question, are we talking about wall compression or storage compression for data files?
Everything.
Everything.
Every single byte must be compressed.
Okay.
Everywhere.
And for protocol as well, I mean for transmission of data when we query also.
Yeah, actually, a few weeks ago, like 2 weeks ago, I had a talk at CitusCon. It was called on compression of everything like that. I think everything in Postgres. So, and this is a talk about different places for compression. And Kirk was talking about that something of it, this can be like applied here, and we are continuing the talk. Kirk proposes the idea of having a dictionary for a column in a table. That's a good idea, but it's difficult to implement online because we have to change parser. We need a way to define this dictionary. We have to change like detoasting. Currently, detoasting and toasting, it's relation wide because toasting doesn't know is it toasting this column or that column. It's just toasting for this relation, and it's a global toast relation for a table. And actually, how things are toasted is very, very deeply ingrained into what is datum, like into notation of passing different values here and there inside the Postgres core. So I was thinking how to do it, and it seemed like difficult idea. Next idea was to do online system-wide dictionary. Let's introduce one dictionary that will be compiled in, and like it is defined when you configure your build. And whenever you do initdb, you already have this dictionary entrenched into binaries. This is a good idea. Maybe we'll go there. And the last idea, the simplest idea I got is that we need to compress data that is nearby other data. And one thing came to my mind. Let me show the screen. How to share the screen? Do you see
yes.
code? Good. Let's see how B3 is built. NBT build. I think it's the file is called showing Meson, but it's okay. Let's just go to NB3 and see what files are there. We can find here NBT sort. This is a file that where the B3 is built when we already have a prepared data, not insert one by one. And here we have a logging. It's done by BT BL write page, and it's done by a call that is called log new page. And it is inserting each block one by one, like register FPI. If we go deeper, we can see that at some point it will be compressed. Register block. Yeah, xlog compress backup block. And these blocks will be compressed one by one. But they must be similar. When we are compressing second block, we might reuse dictionary from the first block. And the only thing that we need here is keeping a context of a compression. Like you see here, we're calling a function LZ4 compress, or this standard compress, or PGLZ compress. And both these codecs, LZ4 and this standard, support the mode when they are using previous dictionary for new chunk of bytes. To see how it's implemented, I've just downloaded patches of libpq compression, because there we always pass like new messages that are compressed, like that will be compressed based on the dictionary of previous messages. And here we see that LZ4, like libpq compression, is calling it's decompression. I want to find compression. Yeah, it's calling something that is called continuation. We are not compressing, but we are continuing previously done compression.
Keeping the context, right?
Yes. And I want to try to reuse this function, this code from libpq compression inside wall logging compression. That's the idea.
Between the records or in walls, right? But it should be done for specific table only, or because across tables that is very different. It doesn't make sense. Or
cannot retain context between different records. Why so? Because we are that's about concurrency again. When we are preparing one wall record, we are calling a function that's called xlog insert. Okay, let's. We are calling this this function, and it's not taking any global lock. It's preparing a record in backend local memory, and only when it is ready, it's grabbing wall insertion lock, places these bytes. No, it's not even copying bytes with the log. It's just incrementing xlog. Let's see how it's done. It's incrementing an end position. And then it's doing copying of bytes into a global xlog. So when you are preparing a wall record, you cannot do a compression which is using a context, because context is running concurrently.
So it means that unlike column store databases, we cannot benefit for I mean, we can deal with only with one row. And
yes,
one row consists of multiple fields, different columns. They can have different data, and
we can benefit from compressing only one record. We cannot retain context between different records,
which is very sad, because like the highest benefit can be if you compress a column, because it consists of similar records, sometimes duplicates and so on. Right, but inside the one row, we might have some duplicates, for example, but probability, likelihood is much lower.
But when we are doing index build, we are using huge records with many pages together. That's why I'm looking into the index build.
This is interesting.
because
Yeah, when you were saying record, I wasn't thinking record and structure. I was thinking tuple.
Table.
Right. But what you're saying is this is an amalgamation of multiple tuples into a structure record. And at that point, we can have, the replication of data in such a way that we can get an advantage out of compressing it. Okay. Even though we don't keep that. Now, here's a question for you. Does huge pages make a difference?
Huge pages.
Yeah, like if you're the larger your page, so if you're using a 4K page or whatever, it's like, I don't know if this breaks across these records, or if you're using like, whatever, a megabyte page, then all of a sudden, if you can get much larger records even, and you're talking a megabyte of data, and then you're compressing that, then to me, yeah, I'm just wondering how this is impacted by page size.
We are logging like page level.
Yeah, it's about buffer pool. We talk about. We discussed it's for everything, but now we switch to since it's full page insert. It's about wall already, right? So we went down to the wall.
When we are building B3, we are doing it in unlogged way. First, we are doing it in unlogged way. So let's step back a little. When you have a B3, you are updating many pages on a way of new insert, and each page modification of each page must be wall logged. But when we are building B3 from scratch, we are sorting data and building index totally unlogged. And then when it's totally ready, we are wall logging a whole file from the beginning to the end. We are inserting it into wall stream, and then it is duplicated to every standby and added to like point-in-time archive, point-in-time recovery archive, and so on. So the idea is that normally when we are modifying the database here and there, we have a very, very small wall records. Wall record is one piece of restoration, one piece of a change inside the database. But when we are wall logging newly created index, we are wall logging a huge piece of data together.
Good.
And we could benefit from compression context, but we are still doing it. We still restart it for every single page because a compression code here is not aware of retaining compression context.
So what you did, and I didn't recognize it early on, is by choosing the index, because it gets written at the very end, okay? And it's going to be written basically in order is a good way to see it. So you're going to write all the data of the index, and you're going to shove that through into the wall file. Now, by turning on this carry forward context concept, what you're doing is saying, hey, now we have a great point. This doesn't work for a lot of other things, but at least for create index, maybe we can reduce, in some cases, maybe the size of what we're logging by 60 to 80%, right? Because a lot of indexes have tons of duplicates, kind of thing, depending on how much that goes. It could be 50%, but a 50% reduction in wall every time you create a large index, I don't know, that seems valuable.
I don't think that we will get such big numbers because it's already compressed. It is compressed by 8 kilobyte chunks, and when we were doing benchmarks of Z standard and LZ4, we didn't saw big difference between LZ4 and Z standard because 8 kilobytes is enough to be like to do a decent compression, but not enough to unwrap full strength of Z standard. this standard is better at compressing long ranges, like 100 kilobytes or so.
For example, if we are able to keep context and benefit from like vertical compression, columns. Okay, I'm like this is like always like this is infinite topic from especially like I see the pressure from column storage databases here, because when they say, I recently had like small discussion with CTO of Victoria Metrics saying, oh, 1 terabyte or gigabyte or 1 billion rows. I say 1 billion rows is terabyte. They say 1 billion rows is gigabyte, right? And it's like 3 orders of magnitude difference in our impression of how many rows we when we say like this is what to expect, right, in terms of storage. And of course, if you can compress columns, it's much more beneficial. So yeah, but here we discuss some adjustments that everyone could benefit from transparently, right, in terms of
absolutely.
Yeah, that's also super interesting. And we have comments in chat. Let me bring them. First side question, does compression use information from table statistics, that one which is gathered by analyze?
Compression of wall, no, it's just taking a block here and returning block here with a new lens. Nothing is used, nothing is passed to compressor, unless resulting lens is more than it was originally. So if a compression is useless, it's returning false.
So we don't compress things if the performance is bad. If it makes it bigger.
Not the performance, like in terms of time per byte.
Yeah. If the size gets bigger, then there's no reason to compress it.
If the compression actually blows things, it's not used.
In this case, we already spent some CPU cycles for this compression attempt, but we save on future decompression.
We must get this result, and some codecs actually take it into account. Like PGLZ knows that it can fail. For example, LZ4 cannot fail; it must return a result. The standard cannot fail; it must compress to the end. PGLZ knows it can fail, and if it sees the result is just too big, it will return false. Sorry, I didn't compress the things because things seems to be too big.
Not this time, right?
yeah, it's kind of optimization that is not useful in general purpose compression. And there are many such cases when typical interface of codec of coder and decoder is not suitable for databases. For example, in analytical databases, do you remember that store? That was an extension by Heikki and friends, maybe by Pivotal or VMware, someone from there. So they were like compressing columns on Postgres pages, and when they were adding some tuples to existing page, they had to extract it fully, add few bytes at the end, and then compress it again. Because no codec is currently supporting recompression. You cannot add few bytes at the end of a compressed slice. You have to extract. And that might sound not actually that scary as it actually is. Compressed page can be really huge when it's decompressed. It's 8 kilobytes of compressed data, but when you decompress it, you easily get gigabyte or a few gigabytes of decompressed data because it's compression, it's effective, but it's not effective when you want to add something. And when I will have enough spare time, I will go to LZ4 or Z standard and implement something like compress few bytes to the end of a compression chunk, compressed chunk.
But here's one for you. My understanding of how we end up storing these bytes is obviously we changed the bit width of the corresponding bytes that we're storing so that we can actually have a way of encoding normal bytes versus in dictionary words, right? The dictionary words get effectively a high bit and a number attached to it. So if you go at any point in time and you want to add ABC to the end of a compressed string, why not just convert the ABC to the correct bit length at that point, and then treat it as though it's unencoded, i.e., don't set the dictionary lookup, set it as a new incoming byte, and don't even try, since it's a small string at the end of something compressed. That would be I wouldn't bother trying to decompress it to add something small. Now, this suffers because if you add ABC to the end of the string 500 times, obviously you're not getting the benefit of compression of those 500 times of adding that. But you don't suffer this massive decompression and recompression to do a small add. So
it's doable, but the problem which you encounter, I think that the technique might work, but the problem is that you need synchronization. At the end of the compressed stream, if you do not work decompression from the beginning, the problem is not that you don't have that dictionary. The problem is that you don't know which byte is a control byte. Like some bytes are telling this part of information is literals, like take these bytes as is, or these bytes are match, and match is a reference to dictionary. And when you are looking at the end of a compressed stream, these bytes do not look different. They all have high entropy. They all look like a mess.
Oh, well, that's my confusion. And again, I when I read most of this stuff, it was probably freshly written because I'm older. But yeah, my understanding is as long as you knew the bit width, you could extract a given byte, and in each byte it indicated if this was a lookup byte or a count, right? Because typically there's a pseudo run length encoding concept in that where it's like, hey, we're actually writing out, there's a control thing that says the next string, whatever you have, there's 7,000 of them. And then the very next string could be a reference to a dictionary string of the word director. And then it would be 7,000, the words director repeated in a row. And maybe I misunderstood that. Maybe they're actually doing that with more bytes than that. Whereas the end of the string, the other problem becomes, though, is you could throw off the dynamic building of any dictionary strings if you just appended the way I said. So I'm willing to say it might have been a bad idea. As always.
For example, in PGLZ, we have a concept of a so-called control byte. And this byte is telling that it's actually a bitmap for next 8 actions. One action might be match. Let me find the documentation for this. Match.
There's a list there, like good match and so on.
Let's see how decompression work. Decompress. So when we are doing decompression, first you locate the first control byte and start it from each bit. and this bit might mean match tag, or if it's 1, it's a match tag.
Yep.
And if it's 0, it's a literal byte. Output control byte, literal byte. And the match tags are they can have various different lengths. So you can predict the place of a next control byte if you know total accumulated length of every match. But to compute it, you have to you don't need memory for decompression, but you have to do actual summarization of lengths of every match to know the position of a next control byte. And when you are at the end of stream, you have no idea when was previous byte. In video codec, they have idea of resynchronization. They are injecting some hash values that you can recognize that they are not part of a data stream, and you have a video compressed stream at the middle, and you know this is the keyframe. I can start streaming from this frame, and that's why it works. But this concept is too heavy for algorithms that are working with 8 kilobytes,
right,
and 4 kilobytes, and LZ4 is sometimes effective for like 100 byte strings, and 100 byte strings is bigger than keyframe in H264 codec. So we don't have this resynchronization stuff. That's why we don't have a recompression at the end right now, but we might have this.
So, but let me follow this for a second. If whatever block I read represents a complete string of data, right? Like for a field, a compressed column value, whatever I get, if I were to decompress that, I know that that last byte somehow is the end of the compressed data, okay? Whether it's covered within a control string or not. So anything you find after that, wouldn't that be a position where you'd find your next control string anyways?
I didn't catch it. Sorry.
Okay, so we have a complex structure, right? So we have this record, and in it, it has a bunch of control bytes and control characters. And I'm thinking of them as like printer escape sequences, if you will. Okay. When I get to the end of this string, it should be complete. Okay. Even though it's the compressed string, it itself should be complete. So the question is, would right after that string, what would make dropping a control string there to say the next piece is literal, just the 0, 0, 0, right? The next piece is literal, and then appending the literal string. So that when you start from the beginning and you expand all of this, you end here at the last piece, then you see a control string immediately that says the next 3 bytes are literals.
What you're talking about is what in computer science is called sentinel end. Like you have alpha ABC, like alphabet from A to Z, and then you have 27th.
Not quite. What I was looking at was the decompression code. Scroll back up. Scroll back up to the top where it makes the if right here, where the and one, control and one. This is what's telling me if I'm in line 716. So at line 716, I'm checking the current control character and one, and that tells me if it's a control character or a literal. And if it's a control character, I could repeat some stuff. The point being is whatever I'm about to repeat, what tells it what it's repeating? Does the end of the string tell it what it's repeating, or does it just keep going until it finds the next control value? Well, that would be hard because the control value would look like anything else, like if it was a number. So the question is, how does it know when it gets to the end of the record? When it's processing, let's say it is processing a control value, right? And it's resolving it. It should be encoded in that. And then that means it's only going to process, let's say the last 4 letters are ABC, like you said. If the last 4 letters are or 3 letters are ABC, then the control processes those. Does it know that it's only processing those 3 letters? Or does it assume it's processing until it gets to the next control type
it is
value?
processing until it's got to the end of a compressed string.
Okay, right. So it gets until the end of the compressed string. So if we were to, so if it processed it to the end of the compressed string, and then we tried to append to it, the next time when it read it, it's going to try to read all of that extra stuff in. The only question is what happens at that transition point where we append it?
Old control byte.
Right, it'll reuse all the old control bytes will be reused, but then when it gets, is there anything, let's say the last thing was let's say the last portion of the string was not under control, meaning the previous control byte was a 0, so that it was just accepting it. If you append it to the end of that record, then those would appear naturally. Unless you're telling me these control things are put every so many bytes. How often are these control pieces? Good.
They are put every 8 messages, like every 8 tags. And each tag is either match or literal. And at the end, we have a incomplete we might have an incomplete control byte.
Oh,
don't have an example here, but still, the control byte might be not finished. Like it can have a few empty bits that are unused.
Okay.
And actually, things are slightly more interesting in LZ4. LZ4 do not have this control byte because parsing individual bits is like too branchy for fast decompression, and they are always alternating match and literal, match and literal. But in Postgres, in PGLZ, we have literal byte here. But in LZ4 we can have a literal byte sequence, and it is it's not limited with any number, so it can be infinite when we at the end of part of literal string, we can continue it with new stuff. And the only bit of information that we need to recompress LZ4 is did we finish with match or did we finish with literal? I think we could fix it by installing 0 length literal at the end every time. So if we finished with match, we still add few bytes to indicate that this string might be recompressed, and if it's recompressed, no, it won't work. Sorry. We have to install 0 length match, because if we install literal, next must be match, but there is nothing to match. We don't have a dictionary at the beginning of recompression.
And,
so basically,
could you remind why do we want recompression? I'm quite lost. Sorry.
That was just just one example when existing compression codecs have interfaces that are not good for databases. They are designed for some generic use, but they were not designed for our purposes.
Mm-hmm.
And this was an example of updating a large, say it's a large compressed toast file, but you're only adding a small amount to the end of that value, that string. The challenge is, as was explained, is you have to completely decompress this thing in order to add a very small amount and then completely recompress it to get it back in. And so I sidetracked this a bit, thinking that because I'm really only familiar with LZW and LZ, not the PGLZ stuff. And I know that they worked from expanding the bit size and doing their controls inside there a bit more. So the thought was, well, hold it, there might be a way for that. But I get, so, but it's a good discussion. This is the complexity. It's not just compressing it when the data first comes in. It's also how do you handle an update? Okay. How do you handle these things? And how do you handle in a way that if you are building a dictionary, this is why I like the static dictionary. Most of these things build the dictionary as they scan the data. The challenge is if you manipulate the data in the middle, the dictionary is somewhat unpredictable. And the whole purpose of LZW is it treats it, the entire file as a string of characters. So the dictionary is completely predictable. And as you're going through the decompression, you can actually create the dictionary to help decompress it. When you start changing that predictability, which a database does by changing the order of where you compress things, that makes another layer of complexity. And it gets back to why they end up switching to column-based ways of doing, because at least then they can control the predictability on any given column. So, and a less variance. All right, sorry about that.
Also, let me bring comments with some huge lag, unfortunately. Sorry, I didn't want to interrupt you earlier. But to be fair, I need to bring comments as well from another person. You can run multi-block compression for multiple blocks inside the xlog rec. Yes, but indeed not across multiple xlog records. A good catch. And then on the comment, you're logging all pages sequentially. The answer, that's not entirely accurate for B-tree. For that, the pages are logged as they are generated, which may not be block order, right? Yeah, good comments, I guess.
I found the problem too, like problem of implementing this idea, because B-tree is logging page. Yes, they are logging as they are generated, but they are using one record for one page. So it's just doing insert of a single block number. But we can slightly change this approach in as it is done in gist build.
You mean change it for B-tree as well, or?
Yes, we can change it for B-tree. Here, look, you see the difference. Here, when the gist is ready, we are doing a new page range, and this new page range will batch this range of blocks into like some number of blocks, 32 blocks at once. But B-tree is currently not batching these pages together. The idea is that B-tree is trying to avoid huge wall records, very big wall records, because very big wall record have to be transmitted between standbys, and they are trying to do small records so other backends can squeeze in and insert some new records into wall stream too. But gist is dropping 32 pages at once in one record, one single record, and nothing emits this record. Actually, 32 pages on 8 kilobytes is like half a megabyte of wall. I'm not sure it's just too big record. Half a megabyte, why not?
No, it doesn't seem that big in today's world.
Yeah.
So you
Well,
think the code, gist code can be better, and B3 could like? I know
B3
there is
could
there is gist
reuse
B3. Like we can build B3 using gist, and in this case it will behave. I mean, but it was. I remember R3 was replaced. Original R3 code was replaced by gist code, but
Yes.
B3 wasn't, right? So it's because of performance, I guess, and maybe
Yes, B3 is much faster and much better. And actually,
maybe
I'm working on making gist better, and I will have
maybe this one of the reasons, no? This wall behavior.
no, it's
No?
just a small
Okay.
problem.
Okay.
I had a patch for building like this is a sorting build. This is a part of a sorting gist build, and this sorting build is not enabled for B3 gist contrib model. I had the patch, and Heikki even committed this patch, but had to revert it because I made a few bugs there. And then I still cannot find enough time to fix.
But this is different topic, right? So
Yes.
so you think for B3 batching to wall, it's also a good idea, right?
Yes, certainly. If we will make like context reuse in wall compression, batching many pages at wall level will be beneficial. Certainly.
And how will it help us with so it's directly related to compression, right? So if it's batched,
Well, yeah, because now when we write, instead of writing one, we're writing 32 pages, right? So if we can bulk 32 pages
compression
together,
can be more efficient.
it's now we're talking a half a meg of data that you run compression over, you get better compression.
That's
or the
interesting.
opportunity.
And B3s are everywhere, so yeah, that's interesting. So it's we are almost 1 hour.
Yeah, and we didn't write any single character of code.
So are we going to touch anything or just discussion? That's it. Let's
do it next time, maybe.
Next time, right?
Yeah. Honestly speaking, I was not like really prepared. I tried to configure my build, and for some reason, LZ4 is not working on my macOS. I don't know what's the problem. So configuration is not seeing LZ4.
Yeah, well, okay, it's fine, I think, but this is very fundamental stuff. Like yesterday, you said I have some simple idea, but obviously it's not
like
simple
super simple, like 2 lines of code, and we will get a working version. But no, we didn't get.
But 2 lines of code, plus we need to change to batching for B3 to benefit from these 2 lines of code, right?
Yes.
Or no? Right.
Yes.
So it's which is already quite interesting, because it may be
we just get this part.
We steal idea from gist. That's it, right?
Yeah. We just take and arrange. That's it. No, it's not. But
5 characters, so 6, right? Okay. Okay. Next time we'll try to get your setup fixed, or switch to Linux, maybe somewhere remote one. Okay. And try to.
It will be difficult to run Zoom on Linux, but I can do it on virtual machine or on JitPod.
Yeah, I mean, this is what this is what I meant. Okay, and we will try to do it. Consider this session as preparation, design session. Okay, it was very good. Deep. I lost myself a couple of times, maybe more. Thank you so much. Okay.
Thank you, everybody.
Yeah. Until next time. Bye.